Okay, we're talking about type 1 and type 2 errors in testing. So here's a grid that kind of describes how this works. Here's the fact. The null hypothesis is true, the alternative is true, and the null hypothesis is false. That's maybe what the truth is. Over here is what the test result is. Reject the null hypothesis, fail to reject the null hypothesis. Okay. So if I reject the null hypothesis when it's true, I've made what's called a type 1 error. And if I reject the null hypothesis when in fact the null hypothesis is false and HA is true, that's correct. If I fail to reject the null hypothesis and the null hypothesis is true, I've done the right thing. If I fail to reject the null hypothesis and the alternative is true, I've made what's called a type 2 error. So in words down here, a type 1 error is to reject the null hypothesis when in fact it is true. A type 2 error is to fail to reject the null hypothesis when in fact the alternative holds. In testing, you can set, oh, here we go, up here, I'm sorry. The type 1 error probability is called alpha, the type 2 error probability is called beta. The alpha probability is controlled in the setup. So it's controlled by what we think an unusual value is, because type 1 error says HO is true, but I reject it because I get an unusual number. And we say we want something to be considered unusual enough, usually at the 0.05 level, less than a 5% chance of seeing that if the null hypothesis is true. That's the alpha. So in testing, you can set alpha to be any value. Alpha is called the significance level, usually set at 0.05. So the type 1 error probability says I reject the null hypothesis when it's true. I don't want to do that. I want to make sure the chance of falsely rejecting that null hypothesis is small at the outset. And then the type 2 error probability is called beta. Now beta depends on what the alternative actually is. So what's the actual value of the parameter? If the true value of the parameter differs from the HO value by a lot, beta will be a small number. So the evidence will be clear, and you will reject the null hypothesis most of the time. Otherwise, it can be large. So you might think, well, you know what, I said maybe I'm doing coin tossing and I think the frequency of heads is 50%. I'm going to toss the coin 100 times, and then if I get much different from 50%, I'm going to say the coin's not being tossed fairly. So if the person tossing the coin is more pretty close to being fair, but consistently a little bit unfair, then the null hypothesis is false, but you won't detect it. If, however, the fraction of the time the tosser gets heads is much different from a half, then if you do 100 tosses, you're going to detect that and you're going to reject the null hypothesis. So the probability of making a mistake depends on how far away the truth is from what the null hypothesis says it should be. So we can't control this unless we know what the alternative looks like. And sometimes when people set up tests, they say, well, I'm trying to detect an alternative that's about this big. And then I can talk about, I know what alpha is, I know what beta is, I compare them. And maybe I want alpha and beta to be the same size, maybe I want them to be at some ratio. So you can control that. Alpha is controlled by the setup, beta is controlled by the alternative that you're studying. But lots of times you don't know what that is, and you're just going to make an assumption. If it's this big, I'd like to find it. What's the chance I miss it? This type 2 error probability is the chance of not detecting something that you're trying to look for. Now you can reduce the errors by increasing the sample sizes, but that costs money. So that's the story on error probabilities. Over here is computing p-values. We still haven't really told you how we're going to decide. It's coming up though. The p-value is going to tell us. So this is going to, these lead us to decide statistical significance. The p-value is a way of quantifying the strength of evidence against the null hypothesis. P-values less than 0.05 make the results statistically significant. So this is where we are. We're going to be looking for that. And we'll say that the results are statistically significant at the 0.05 level. That means if you used alpha equals 0.05, so that you decided you're allowed, the values have to be that unusual before you reject the null hypothesis, where they happen less than 5% of the time if the null hypothesis is true, then we call them statistically significant, and we could set that significance level to be less if we want. But typically the value chosen is 0.05. So somehow the p-values are related to how unlikely the value is, and here it comes. Small p-values cause statistical significance. Here's how they're computed. So to make things a little more complicated, unfortunately, there's 3 ways of computing p-values depending on which alternative you're using. So maybe this is mu is bigger than mu naught. Maybe this is mu less than mu naught. Maybe that's mu not equal to mu naught, like that. Or it could be p bigger than p naught, or p less than p naught, or p not equal to p naught here. Either way, your test statistic, we said it was either t or z, has this kind of a shape. And what we're going to do to compute the p-value is we're going to compute the value of the test statistic. We're going to locate it on the axis. And if it's greater than alternative, we're going to shade right. And the area is the p-value. Okay. Now what happens there is, if the parameter is bigger than, parameter turns out to be bigger than the proposed value, when I compute t or z, I end up getting big numbers. And the bigger, the more extreme it looks, and the more likely it is the parameter is bigger than the proposed value. On the other hand, the more unlikely it is that the parameter is the proposed value. So this tail probability is telling you how unlikely the null hypothesis is to be true. So the alternatives should push the test statistic value out in that direction, and this would be the probability of having it if the null hypothesis is true. So if that gets smaller and smaller, then if that's what would have happened if the null hypothesis was true, and we observe those kinds of values, then we think, hey, the null hypothesis might not be true because those values don't happen when the null hypothesis is true. So this is all the density under the null hypothesis. So what the alternative does, it's going to, if the alternative says the actual parameter is larger, it shifts that density curve over, and so you're more likely to be out here, and the null hypothesis doesn't want you to be out there, and so this area comes out to be small. If the null hypothesis if the null hypothesis was true and you get those kinds of values, those values are unlikely, so you get a small probability in that direction. On the other hand, if the alternative is parameter less than the proposed value, then we're going to shade left, and area is p-value. Okay. So we look at our test statistic value, we locate it on the axis, and we shade left. We get that area. And if that area is less than 0.05, we would declare the result statistically significant at the 0.05 level. And here, the third one is what's called a two-sided alternative, or sometimes called a two-tailed test, because we take this test statistic value, and maybe it's here, or maybe it's up there. It's one side of 0 or the other. And then we take if it's above, we shade over to the right, and we find a symmetric position, and we shade left. Or if it was over here left below 0, we'd create a symmetric position, and we would shade outward like this. And the two tails, as you would say, p-value is the area of both tails. So you get the area of both tails in two ways. One is actually to compute them separately. You take the distance away from 0 that you're at on both sides, and you find the area of the two tails, or you just find one tail and you double that area to get the tail probability for both, which is the p-value. So area is p-value of one tail of one is area is p-value area. So one tail test two-tail test. So one-sided or two-sided alternative. The sidedness says that you're shading in one direction or the other, or choosing just one tail to compute the p-value. And a two-sided test you're looking for two kinds of differences, and when you compute the p-value, you're finding the area of two tails. So a two-tailed test is based on having a two-sided alternative where bigger than or less than is of interest to you. And a single-tailed test is based on a single-sided test where you're only worried about certain kinds of values of the new value for mu or p. Either less than, you shade left the smaller values. For greater than, you shade right the larger values to get the p-value. So that should be a little bit mysterious, and it will stay mysterious for a while, but luckily it's a procedure. And you can follow the steps of the procedure that look like find your null and alternative, compute your test statistic. Based on the alternative, find the p-value. Compare it to 0.05. If it's less than 0.05, you declare the result statistically significant, and you reject the null hypothesis. So those are just steps you do. And the details of why they work, it's a little bit subtle, but the final result isn't that subtle, so it's possible to carry it out. And you can actually ask your calculator just to compute the p-value for you. And if it's less than 0.05, you go, hey, the results appear to be statistically significant, meaning probably not due to chance alone, so probably due to a change in the parameter value in the direction we were trying to detect. Okay, I'm closing off this very sophisticated slide and moving on.